Hello, everyone, and welcome to today's Würth Electronic webinar. I'm your host, Amelia Thompson, and today's webinar is Advancements in WPT and NFC Technology, presented by Deepthi Punacha Makimata, design engineer with the Power Transformers and Custom Magnetics Division of Würth Electronics Midcom in Europe. As a reminder, if you have any questions during today's webinar, please ask them in the questions box, and we will get to them at the end. Now, if your question doesn't get answered, simply reply back to our follow-up email from webinarteam@we-online.com. Because you registered for today's webinar, you will automatically receive the presentation slides and the video on demand in a follow-up email, again, from that same email address, webinarteam@we-online.com. Simply look for the link in your email. And if you go to the handouts section, you should also be able to download the slides for today's presentation. Don't forget to register for next week's webinar. It is derating of connectors, and you can register online at www.we-online.com/webinars. Now let's begin today's Würth Electronic webinar, Advancements in WPT and NFC Technology, partnered with DigiKey Electronics.
And today's topic of the webinar is the advancements in wireless power transfer and NFC technology. I would like to welcome everybody from my side as well. And in today's webinar, we are going to have an overview of how wireless power transfer and NFC technologies work and how we can tap into the advantages of both these technologies to develop a powerful system that uses WPT and NFC simultaneously. And this system implementation will be the highlight of today's webinar. So moving on to the short agenda of today's WPT and NFC advancements webinar, we begin to see how WPT works, what are the recent advancements in WPT technology, where we'll be talking shortly about the standards that governing this technology. Then we move on to the near field communication technology, see how it works, the principle governing NFC, some of the standards, and finally we move on to the system implementation of the NFC and WPT combination system. And last but not the least, there is a small slide showing the product portfolio for these combination coil products offered by Würth Electronic. So let's begin the webinar today by talking about a few examples that we use in our daily lives, which uses wireless power transfer. So the charging earpods wirelessly is one of the most commonly used applications that most of us know today. A second example is that of an electric toothbrush, which has been here for quite some time, and it is also being charged wirelessly. And this helps us eliminate the use of cords and unnecessary cables. The figure 3 shows another example of a charging pad where we can use our phones, our watches and AirPods easily on a single platform without having to worry about using multiple cables for each devices to connect them. And the fourth example is that of a power tool, which I can only imagine will make things easier for people using the power tools without having the hassle of connecting long cables in a construction site and taking it with them wherever they move. So you see, wireless charging has really helped us in our daily lives to eliminate the need of cords and still perform efficient functions. So how exactly does wireless power transfer work? As you can see in the image here, there is a base station or the transmitter at the bottom, and then your mobile device or your receiver is placed exactly on top of the transmitter, and your phone charges or your end application begins to charge. So how does this exactly work? So the base station or the transmitter is connected to the power source, and you have an alternating current which is generated in the coil due to an oscillator in the circuitry from the power source. This alternating current then generates a magnetic field, which induces a current in the secondary side or in the receiver side. And by the principle of electromagnetic induction, the mobile phone or the circuitry at the end application charges and uses the current then to charge the application or other the electronics behind at the end user application. So this image also describes the same function, and as you can see, the magnetic field is concentrated exactly at the center of the device and in a small space. And it has a small limitation that the mobile device or your end application has to be placed exactly on top of the transmitter with a very small distance between the transmitter and the receiver for efficient energy transfer. So the typical frequency range at which this wireless power transfer works is usually from 100 kilohertz to 200 kilohertz. The powers capable of transmitting wireless power is up to a few kilowatts range, depending on the application. And the type of communication that's possible is a low in-band communication with data rates of approximately of up to 1 kilobits per second. So it's very important to make sure that the mobile phone is aligned correctly on the transmitter. Otherwise, due to some small misalignments, there may be a loss in efficiency and your phone might not charge so efficiently. So from this, you can already deduce a few advantages and disadvantages to the wireless power technology. So here we see a few of the highlights of the advantages and some disadvantages from WPT. What are the advantages? The advantages are that, as we have already seen in the previous slide, high power levels up to some kilowatts is possible. No wear and tear of charging cords due to mechanical stresses of daily plugging and unplugging it. And it enables easy, hermetically sealed designs so that we can keep out environmental factors like moisture and protect the devices inside, and also eliminate the need for having connectors and power ports. The disadvantages are that there is very low data rates possible to transfer of only up to a few kilobits per second, and it's inefficient to transfer power over long distances, because then we lose energy in the form of heat and it is not very efficient. So keeping these advantages in mind, we will see in the future slides how we can use it to our advantage to combine it with the advantages from NFC technology to build our more efficient system combining the two technologies. So like every standard or every technology that is developed in the world, there has to be a certain body that is governing the standards or defining a set of rules of how this technology can be safely used for everybody in the world. Since wireless power technology is growing at a rapid pace and many people all over the world are using wireless devices, standard body was developed to define a certain standard defining some rules for how we can use this device or this technology easily to be compatible with every device and safely used. So one such body is the Wireless Power Consortium, and they are defining the standards for many different types of wireless power applications. Here we talk about two main standards developed by the Wireless Power Consortium. The CHI standard, which is the standard developed for mobile phones and handheld devices supporting up to 15 watts of power, and the KEY standard, which is the standard for delivering 2.2 kilowatts for the kitchen appliances, which we see here. And the symbols shown on figure 7 and 8 are symbols for the CHI standard and the KEY standards. So if you see any appliances with these symbols on them, then you know that they are CHI certified and they're safe to use and they're following certain norms defined by the WPC. The specs of the CHI standards is as follows, that the operating frequency is at around 87 to 205 kilohertz. And there are three basic power profiles defined by the Qi standard. That is the basic power profile for wireless charging devices capable of delivering up to 5 watts, the extended power profile, which is capable of delivering power up to 15 watts, and the magnetic power profile, which is capable of delivering power up to 15 watts. So in the next slides, we see how we can go a little more deeper and what are the advancements in the Qi standards. So this year, the Qi 2 standard is going to be released, and the preliminary specs are already in discussion, and the WPC will release the Qi 2 standard specs very soon to the public. And we will be talking a little bit here about the Qi 2 wireless charging. So what is new in Qi 2? So the magnetic power profile is one of the highlight of the Qi 2 standard, and that the highlight is that the magnets are used to align the transmitter and the receiver coils. So if you remember in the earlier slides, we spoke a little bit about misalignment. And in this case, the magnets here are present on the transmitter and receiver coils, and they will help to align the two devices, your receiver and the transmitter, exactly on top of each other. But the Qi 2 can also include products that have no magnets as well. And the operating frequency in this case is defined at 360 kilohertz instead of the 205 kilohertz that we observed in our Qi standard. And the MPP, or the magnetic power profile, offers guaranteed 15 watts power delivery. The symbols that you see on the figures 9 and 10 are then the symbols for the Qi 2 devices. And in the future, when you will see these Qi 2 symbols on your devices, then you know that they are Qi 2 compliant. And this was about the Qi 2 wireless charging. Next, we see what is exactly the advantage of the Qi 2 wireless standard that is developed. What's new here? How is it going to help us? Or how is it better than the Qi legacy power profile? So the Qi standard, which was developed earlier, we call them as the legacy power profiles. That is the BPP up to 5 watts and the EPP up to 15 watts. And as you can already see in the images, the previous legacy power profiles, in the case of these power profiles, the charger had to always be placed on the table and the phone had to be aligned exactly on the charger. And if there's a slight misalignment or if the phone slips off the charger, then it would not charge anymore, or you could not use your phone along with your charger when it is charging. And with the new Qi 2 power profile, with these magnets in place, the transmitter holds on to the receiver device or the phone, as you can see in the image, and it helps to align the phone and the charger perfectly onto one another, and this makes it more efficient. So in this image, you can see if it is less aligned, if it is not aligned as shown, the coil is below and the coil on the phone is the blue color coil, and you see the misalignment between the two arrow marks showing the center points of the coils on the transmitter and the receiver, and it is less efficient. And when they are exactly aligned one on top of the other, then they are more efficient. So this itself is a big advantage with the Qi 2 power profile. And the magnetic power profile is of course adapted from the MagSafe power profile from Apple, but it is not exactly the same as the Apple MagSafe profile. And the MPP is an open standard which everybody can use in their or adapt in their transmitter designs. Some of the advantages is that it's 4 times faster authentication compared to the Qi proprietary standard, and the magnets which are used to align on both the sides, the transmitter and the receiver sides, it can align within 2 millimeters. And it is key fob friendly. That means they have less interference with the Qi 2 due to the 360 kilohertz operating frequency. So the 360 kilohertz operating frequency was defined so that it was seen in the past that other devices around a Qi compliant device was creating some kind of interference because of the operating frequency range, and especially key fobs. And at 360 kilohertz, it was observed that they don't have so much interference with the Qi compliant devices, and so this particular frequency was then adopted. So having seen the advantages of Qi 2 and what is new in Qi 2, and having had a small glimpse about the magnetic power profile, let's see how the magnetic power coil actually looks like, or the MPP transmitter coil actually will look like in the future. So here is a coil that is developed by Würth Elektronik, and this is an exploded view of our coil. This will be available soon on our product profile once the specs from WPC has been made public. And you can see that there is a bottom enclosure and a top enclosure. Then there are two magnets. So the magnet on top is an array of magnets, which is then supported by the permeable magnet shunt. This is on the transmitter side, and we have a similar magnet structure on the receiver side in the end application. Then the coil itself, which is made out of Litz or Litz wire, and then the ferrite, which has a slit in between where the leads can have an output from the coil. So this is the breakdown of a MPP transmitter coil, of how it would look like then in the future chargers which adopt the Qi 2 standard. So it was a brief introduction and overview of how WPT technology works and what are the advantages of the WPT technology and the standards governing the WPT technology. Now let's begin the NFC technology overview and see how the NFC technology or the near field communication works. So some examples, let's begin with some examples to familiarize for those who haven't heard of near field communication technology. So some of the examples you may have observed is you have a boarding pass loaded on your phone and you use this to enter your gates or make some payments. You have your card information stored on your phone and you use this to make payments. And you have some other passes or e-tickets on your phone and you use them to access them. So all of these technologies work on NFC or near field communication. And this NFC technology is also a short range standardized contactless communication technology, but it is short range in the sense it can have a distance of separation of up to a few centimeters. In the WPT technology, the separation was just a few millimeters, and in this case, it's a little bit longer or more than the WPT technology. And the frequency band also is responsible for this. As you can see, the NFC operates at a frequency band of 13.56 megahertz, and the WPT operated only up to 205 kilohertz. The charging powers, however, in the NFC technology is only possible up to 1 watts, and the data rates is usually between 106 kilobits per second and 424 kilobits per second. So the properties of NFC include very fast startup, and power sensing. So when you're using your phone to make a payment, it usually happens very quickly. You just tap your phone onto the card reader or the payment device, and the transaction is already completed. And this is the remarkably fast startup operation. And the short operating distances also guarantees more security, and it has small data payload. So this was about how an NFC technology is used in our daily life and some highlights. From this slide, we can already determine some of the advantages of an NFC compared to the WPT technology, but we will come to this in the later slides. So what exactly is the end principle or operation principle of NFC technology? So in this block diagram here, you can see that we have a contactless reader, which is operating at 13.56 megahertz. and a secondary device or an NFC tag, which is then the receiver side. So here we have in NFC, we call the transmitter coil and the receiver coil simply as primary antenna and secondary antenna. And the transmitter side is usually called the NFC reader, polar, or initiator, and the NFC tag is then the listener and the target. So we get these are the different names then used for the receiver side. In this case, the contactless reader just communicates with the passive component or the NFC tag by electromagnetic fields, and it also powers up the microchip that is present in the NFC tag, and there is data communication that happens. So the when you place your card on the contactless reader here is powering up your microchip in the NFC tag and gets whatever information it needs from the NFC tag, and the NFC tag then sends the data through the electromagnetic field to through the primary antenna to the contactless reader. So since the contactless reader is powering up the NFC tag, it is called as the active component, and since the NFC tag itself has no power source, it is called as a passive component. So this is exactly how your contactless tags or your smart cards function. So having seen how NFC technology works, let's go a little bit deeper and look at the basic 3 modes of operation for near-field communication. So we have around 3 main modes which are used for near-field communication, and they are the read or write mode, the card emulation mode, and peer-to-peer mode. So in the read or writer mode, the NFC enabled initiator, like your mobile phone or the card reader, will just read or write the information from the tag or the contactless reader and get the information from the tag. In the card emulation mode, the NFC device behaves like an contactless card using one of the standards of NFC. And in the peer-to-peer mode, we can establish a 2-way communication where both the NFC-enabled devices are communicating with each other. So there is bidirectional transfer of data between the two. So to give a better idea about these 3 modes, we have a pictorial representation of how these modes actually work, or what are the daily life examples that we have seen. So in the peer-to-peer mode, it's this is an NFC-enabled device, and so are these. So there is data communication that's happening between the 2 devices, and they both are active because they both are using power sources and need power, and they're transferring data like images or videos between each other. In the card emulation mode, your phone itself emulates the behavior of a card, and you can use it to make payments or to go through a gate with your boarding pass or to load some e-tickets. So that defines your card emulation mode. In this case, your phone is your active device and it is just emulating the behavior of a card. And in the read or write mode, your phone is then your NFC enabled device, and this is just reading the tags that may be present on an expensive wine bottle or on a coffee shop and getting some data from these tags. So this is the 3 modes of operation where NFC is very often used. So similar to the WPT technology, the near field communication also has a body which determines certain standards. It is called as the NFC forum. And here you can see there are typically 5 standards which is defined, but the highlighted red box indicates the most commonly used standard. That's the type 1 ISO IEC 14443A. This is the standard which we are also using in Würth Elektronik, and it operates at a frequency of 13.56 megahertz, and it has a modulation from the reader to the tag, which is the amplitude shift keying modulation, which we are using, and from the receiver to the transmitter, again the type of modulation is then the load modulation, which we are using. So now at this point, we have gone through the advantages of the WPT technology and the advantages of the NFC technology. And to make a short points about the advantage and the disadvantage, the advantage is that in WPT we can transfer some high powers of up to some kilowatts, whereas in NFC technology we can transfer data rates of up to very high data rates of up to 424 kilobits. But the disadvantage in WPT is that it has low in-band data rates of up to just 1 kilobits per second, and in the NFC up to 1 watt. So overcoming these disadvantages in both the technologies, we are using the advantages from the two and combining it to form our own system implementation, where we use NFC and WPT together simultaneously. So in most of the systems that use WPT and NFC together, it is usually a slotted operation which takes place, where either WPT is turned on and NFC is switched off, or when NFC is active, then WPT technology is switched off. But in our case, in our system implementation, we have used the NFC and WPT technologies together simultaneously. So to explain the block diagram, the red arrow here shows the WPT technology or the WPT system that we have used. This is simply the modules from our own 200-watt development kit, which you can easily find on our Würth Elektronik website. You can download the files and take a look at our 200-watt development kit. So the transmitter and the receiver modules are from this kit. The green arrow then shows the NFC technology block, and we will go block by block. So first we start with the initiator and then the NFC target to see what exactly are there in these blocks. And we have used our very own combination coil, which has both NFC and the WPT part. So on the figure 16 here, you can see our combination coil, which is also available in our product portfolio. So the NFC antenna is just wound around the WPT coil, and that is the specialty of the combination coil from Würth Elektronik. So then the NFC initiator block. So we begin with the NFC initiator or the transmitter side of the NFC part. Here we have just used the normal microcontroller, the Arduino Mega microcontroller from Atmel. The NFC interface is the Adafruit PN532 NFC RFID shield, which is based on the chipset from NXP. And the time of flight sensor is also from Adafruit. It uses the I2C protocol, communication protocol, and it measures how long the light has taken to bounce back to the sensor. And the microcontroller is then powered up externally by the 5 volts DC supply. Then we take a look at the NFC target. The NFC target has almost the similar configuration as the NFC initiator, but the only difference is that the microcontroller board here is the Arduino Uno revision 3, and the NFC interface is similar to the NFC initiator, the same chip, and the display board is from Adafruit, which also uses the I2C communication protocol. And also notice here that the microcontroller is not powered up externally, but in fact it is using the power that is going to be generated from the WPT technology to power up the complete NFC target side. So the complete NFC interface and the microcontroller is going to be, and the display is powered up by the wireless power transfer, energy coming out of the wireless power transfer. And here you can connect your own load, like a DC-DC converter, for example, and use it according to your application. So finally, we come to the filter matching network. The filter matching network is a very important part of the NFC initiator and the target. It is basically used to match the impedance of the NFC antenna to the interface of the NFC chips that is present at the NFC interface block. And since the output of the NFC interface or the chip of the NFC interface is differential, we made our own differential filter matching network, as you can see in the image here, which has a second order low pass filter, then the capacitive impedance network matching network, along with some damping resistors and an equivalent antenna circuit which represents the NFC antenna. The complete description of how we can choose the values for the capacitors and the inductors and how we can build up the circuit can be read on our app note 84 on our website. And the impedance matching is very important, otherwise we cannot transmit the energy to at this distance what we are trying to achieve here, and we would also have a lot of power loss. So then we go on to the next slide. So yeah, so here we see the software workflow for our VPT system. The writing a request from the initiator is from the target accepts the request. So we start by writing a request. The initiator writes a request, and then it's passed on to the target, and the target then accepts the request. And the time of flight sensor then sends the data to the initiator of the NFC interface. The sensor then writes the data onto the target, and at the target side then it is displayed on the display that we have connected, and then it pings the initiator again for the next request. And this happens every few seconds, where the target then receives a request and accepts it, and the time of flight sensor then measures the distance and then displays it on the target side. So the software workflow is also very simple, and it is already adapted by Adafruit, but we had changed it to according to our application. So yeah, it's very easy, and it's easily adaptable to your system as well. So here I have a live video implementation that I would like to play and show of how this system actually works. And here you can, as you can see, the microcontroller is present at the transmitter side, and it is powered up. Let me just change my pointer. Yeah. So the microcontroller here is powered up from the initiator side with the 5 volts, as we saw in our block diagram. Then we have the NFC side, or the NFC board on the initiator side, the NFC interface with the NFC chip on it. And then this is the transmitter side from the 200-watt kit, the receiver on the 200-watt kit. Both the coils are placed in the center, where we have the transmitter coil at the bottom and the receiver coil with the ferrite facing towards the up. And in between, we have a distance of separation of around 6 millimeters. We've used plexiglass as a separation material between the 2 coils. And the green PCBs are the filter matching network that we have used to match the 50 ohm impedance between the NFC interface and our NFC antenna. And on this, on the right side is then the microcontroller for the receiver, and you notice that there is no power cable powering up the microcontroller on the receiver side. The load of the receiver from the 200-watt kit is also connected to the NFC target side, and here is the display board from Adafruit as well, and this is also powered up from the wireless power energy, wireless power transfer that is coming out of this kit. So, and here is our time of flight sensor, where when you place an object close to it, then you should see on the display a certain distance at which the object is placed. And yeah, so let's go back to playing the video. So now you see when you place your hand close to the sensor, then you can see the value here on the display at what height the hand is being placed. And when you move your hand, then it shows you the variation in the distance as well. Let me play it one more time. Okay. So after the implementation, here is a small tabulation of the results or what type of kits or coils that we have used for our experiment. The type of the WPT is our 200-watt development kit. We have simply used the transmitter and the receiver modules from this development kit. The transmitter and the receiver combination coil with the NFC antenna is the 760-308-101150 standard coil, which is also available on our product portfolio in our website. And the distance of separation that we have used here is 6 millimeters, which we achieved by using plexiglass spacers in between. The NFC data rate here is only the most basic, the standard NFC data rate, 106 kilobits per second, and the error rate, what we measured was less than 5%, which is really quite good. And the reflection coefficient, what we achieved with our filter matching network is minus 35 dB, which is also a really good matching reflection coefficient. And the future work, what we take from this system implementation that we can optimize is the system to achieve better data rates from the NFC side to achieve around at least 424 kilobits per second, so we can send more data. And another optimization would be to adapt the filter matching network, the initiator side or the target side into one single PCB and build everything on one single board, like an add-on board which is compatible to use with a WPT system. So here is a small product portfolio of our NFC and WPT coils which are available. And these are the most commonly used combination coils for various power levels and various inductance values, which you can check on our on our website and take a look which suits best for your application. Here are some useful links for the wireless power and NFC technologies. Here are the app notes which are available from our website, the impedance matching for near field communication. It's a very interesting app note with the filter matching network described of how to build the differential filter network, the proprietary wireless transfer solution for high performance, including data transmission, which is based on our 200-watt kit development kit, the high power wireless transfer for industrial environment. Here you have some examples of how you can build your own wireless power system for different power levels using a basic Royer converter circuit or bridge rectifier circuits. And what are some important considerations when you are building your own wireless power system. You can see this in the wireless power charging coil changing considerations app note. And the two most important app notes are the last two, the design and optimization of the simultaneous wireless power transfer and NFC system, which we just took a look at in the video, and our system implementation, and also the circuit and antenna design of a simultaneous wireless power transfer and NFC system. All these app notes and papers are available on our website to take a look at. So please do take a look at it. And if you have any questions, you can write back to me or to our wireless power team at Würth Elektronik. And I would like to thank everybody who attended the webinar. I'm really sorry for the technical difficulties that we had in between. And I hope you enjoyed it and learned a thing or two. Thank you.
Thank you very much, Deepthi, for presenting today. We are going to take a look at our questions that are rolling on in. Again, if you have any questions, just ask them in the questions box. Our first question here is, why is the wireless charging frequency defined only between 85 kilohertz to 200 kilohertz?
So usually the Wireless Power Consortium has defined this frequency range, and the main reason is because at lower frequencies, the efficiency of wireless transfer is better, and at higher frequencies, then we have to take into account many radiation losses and other losses that come into the picture. And this is the reason we are using low frequencies for wireless power transfer to build a more efficient system.
All right, thank you very much. Our second question here, we will be answering just a few more. And again, if your question doesn't get answered during our Q&A session here, we will respond to you directly after the presentation. Our second one here, is Apple's MagSafe charger the same as the new MPP coil design from Qi 2?
So the Apple's the MPP coil is actually derived from the design of the Apple MagSafe technology, but it is not the same exactly. And the Apple's MagSafe design is proprietary design of Apple, whereas the MPP coil design is open to everybody to use. And yes, so this is the main difference, I would say.
Excellent, thank you very much. Quite a few questions are coming in. Our next one here, how does NFC differ from other contactless methods?
So the NFC technology differs from for example, from Bluetooth or Wi-Fi technologies in the fact that the frequency range, for example, is 13.56 megahertz. And also it is very fast compared to Bluetooth and other type of technologies, and much safer, I would say, because of the short duration where you can just tap your phone onto the contactless reader or your payment device and your payment transaction is already finished. So this is also very secure.
Yes, it makes paying for everything so much easier.
Yes.
Sometimes not in a great way either. Our next question here is, what data rates are possible with the WPT systems?
With the WPT system, very low data rates are possible, only up to a few kilobits, and that the reason mainly being the frequency range as well. Since it's in the kilohertz range, it's a very low data rate is possible. Up to a few kilobits is what I would say, kilobits per second.
Very low indeed. Our next question here is a very popular one. What is the definition of rated currents?
So rated current is actually the most safe operatable value of the device before it goes into saturation or gets destroyed, I would say. And this is not very openly written in most of the data sheets. It's usually the saturation current which is mentioned, but the rated current is usually the exact value of the device which it can operate in, the safe value of the current that it can operate in.
Excellent, thank you so much. Our next question here, and then I believe we will be wrapping things up. Again, if you didn't ask a question, you can simply reply back to our follow-up email. That's webinarteam@we-online.com. We will make sure to get every question here answered. Our final one, on the possibilities of integrating NFC with high power WPT system greater than 10 kilowatts, what are the most important considerations when designing WPT coil and NFC NFC antenna?
So the most important things here that you have to keep in mind is to find the right operating point between the NFC and the WPT system. So sometimes when you are bringing up the system with both the technologies inside, You have to make sure you have a good operating point, which is defined by the coupling factor between the receiver and the transmitter coil. This is again defined by the separation of distance. At a particular distance, the NFC technology might not work so well. So to find that sweet spot between the two technologies is very important. And if you are using the very high power levels, then you have to define the, first of all, the frequency of operation for your WPT system, and make sure that your WPT system works perfectly at this particular operation frequency, and you have a very clean sinusoidal wave form without any distortions due to the load modulations on either side, the transmitter or the receiver side. And then you have to bring into the NFC into the picture and build up a filter matching network that will also remove harmonics and other disturbances, and give you a perfect operating point between the two technologies.
Excellent. Thank you so much for presenting today's webinar. We are going to be just wrapping up our Q&A and the rest of our webinar session today. Thank you so much.
Thank you. Thanks a lot, Amelia.
And again, if you have any questions, simply reply to our follow-up email. That's webinarteam@we-online.com. And you can also follow Würth Electronic or myself, Amelia Thompson, on LinkedIn to learn about all upcoming webinars and our podcast. It is the Würth Electronic What's Up podcast, where each week we are taking application notes, blogs, press releases, and of course our webinars and transforming them into an MP3 and MP4 format. The What's Up podcast is found on all podcast streaming networks like Spotify, Google Podcasts, iTunes, and so much more. So join us for next week's webinar. It is derating of connectors. You can register online at www.we-online.com/webinars. I'm Amelia Thompson, and I hope to see you soon.